Okay, now for acetic acid, we have to consider things a little differently. So the only difference in acetic acid is the oxidation state of one of the carbon atoms, right? Because that's the only number that's changing in both compounds. If we compare it up here. So every oxygen atom is still -2, each hydrogen atom is still +1, and one of the carbon atoms is the same because the bonding in the carbon atom didn't change at all. You're still connected to a carbon and 3 hydrogens. So now we go here. So in general, if there are more oxygen atoms attached to a carbon atom, we say the oxidation number increases. So that is what we call oxidation. So you're getting about, okay, we add oxygen to something, it's going to increase its oxidation number. So, and if there's more hydrogen atoms attached to a carbon atom, we say the oxidation number decreases. And we could kind of see this trend in our previous example here. So scroll back up. See here, the more as you add more oxygen atoms, the carbon goes from +2 to +4. Oh, shoot. Don't want to do that. Sorry. Okay. And then as you add hydrogen atoms, it will cancel out the presence of the oxygen atom. So that's why carbon here is 0. And as we add more hydrogen atoms here, the carbon is going to be more negative oxidation state. And then once we fully replace all the oxygen atoms, carbon is in its highest oxidation state, -4. So carbon can have a wide range of oxidation states from -4 to +4. Okay. So the only difference here is you have multiple atoms between the carbon and oxygen atoms now. So when there are multiple bonds between atoms, we imagine that there are actually 2 physical bonds attached to it. So we assume that like COO, say for this example, right, formaldehyde, we assume that we're going to imagine it looks like this. Okay, so when we break it up, we're going to have carbon with 2 electrons here. H has no electrons. And then oxygen is going to have all the electrons from the bond that it was attached to with the carbon atom. So you see here how those 2 bonds now are gone. So we assume that when we take those electrons away, carbon will have a deficiency of 2, so it'll have an increase in it'll have a charge of +2 from the oxygen atoms, but then the -2 from the hydrogen atoms will make this one neutral. Okay, so we assume that there are 2 physical single bonds attached to the same atom. Okay. So for the carbon atom attached to the oxygen atoms, we say there are two carbon-oxygen bonds, and so the oxidation is +3, and so we have a situation of, so there's now 3, so we assume that there are, I don't think I meant to say 2. So for the carbon atom attached to the oxygen atoms, we say there are 3 carbon oxygen atoms, right? Because the double bond counts as 2 bonds to carbon from oxygen atoms. So the oxidation state is +3. +1 times 3. Okay? All right. So let's do some practice here. What is the oxidation state of each atom in propanol? So let's write the structure for propanol. So propanol, it looks like this. Propanol is I honestly don't know where you can find propanol. Yeah, I'm not really sure. I just know it's a really important chemical in industry. But other than that, I don't know where else you may find propanol. Maybe in some type of like heating or something, or maybe well, it's isomer. Isopropanol is found in disinfectants like rubbing alcohol and like any disinfectant wipe, pretty much. It has a very particular scent to it, so you can't mistake it. But propanol is not the same. It's not that. It's an isomer of it. Okay, so here's the skeletal structure. Let's center it a little bit. So that's propanol. All right. Now let's do our same analysis here. We're going to break up the electrons and put them around the most electronegative elements, so they go around carbon, between the hydrogens and carbon atoms, and then it'll go to the oxygen between the carbon and oxygen atoms. Okay, so if we calculate the oxidation states here, let's calculate the oxidation states. We did it for the same thing here. So XA, the same equation, carbon. There's 4 electrons. So 4 valence electrons around carbon. But there's 5 electrons, well, not 5, 7 electrons around it in the compound based on our oxidation state model. And so that's a -3, 4 minus 7, -3. And carbon B, there's going to be 6. So 4 minus 6, -2. And then lastly, carbon C here, there's 1, 2, 3, 4, 5. So 4 minus 5, -1 in this case. So all 3 carbon atoms have different oxidation states. Okay, and that has to do with the fact that some carbons have 2 hydrogens around it, some have 3, and then some have 2, but also an oxygen atom, so the oxidation state will change based on that. Okay, so we'll have a lot of practice, I think, in discussion this week to talk about oxidation states more. But if there are any questions, feel free to contact me. Okay, so now let's go over reviewing by doing some practice problems here. So let's do some examples. How do we know a reaction is a redox reaction? Well, you can't just look at it and say, okay, this is definitely a redox reaction. No, you probably can't do that. Some reactions, if you kind of just glance at it and say, okay, there's no way this is a single replacement, there's no way this is a double replacement, and there's no way this is an acid base, so it has to be redox. You can kind of do that, but to make sure you're right every time, you want to assign oxidation numbers. Okay, so for magnesium is by itself, so we have 0. That's a 0 oxidation state. Remember, for metals and diatomics, that is always 0. Oxygen, also 0. And the rule here is elemental form. Okay? Oops. So when we have the elemental form of an element, it's always going to be 0. Okay? Always 0. Products. So now we have a product that is no longer a pure element, it's a compound. So magnesium oxide, typically, remember, when we assign charges, magnesium oxide O is -2 and magnesium is +2 when they form ions. So we're going to say magnesium +2, oxygen -2. So is this a redox reaction? Yes. So this is a redox reaction. Okay? So what is being oxidized and what is being reduced? Well, we see the magnesium is going from 0 to 2, and the oxygen is going from 0 to -2, so we say magnesium is being oxidized. So it's losing electrons to oxygen. Okay? So in this case, and then oxygen is being reduced. So it's gaining electrons from magnesium. Okay, so we can classify these. We can classify each of these reagents as each of the reactants as an oxidizing reagent or a reducing reagent. So they may sound like familiar terms. So usually the most common oxidizing agent is anything with hydrogen, like hydrogen peroxide, oxygen. So they're good oxidizing agents because they like to be reduced. So in this case, we call oxygen the oxidizing reagent. Okay? And the oxidizing agent is another term for saying, or the species that causes oxidation in another species. Okay? So think of it this way: the oxidizing agent is not the thing that is oxidized because it's causing oxidation. So it's a cause and effect, right? It's the effector. It's not the it causes an effect in something else. So in this case, it's causing oxidation in another compound, so it doesn't get oxidized. So the common misconception is, okay, oxidizing agent, that gets oxidized. That's not the case. It's actually the opposite. It's a play on words. The oxidizing agent is the thing doing the oxidizing on something else. So something else is oxidized. So the same thing is for magnesium. If you're being oxidized, then you're causing something else to be reduced. So this is the reducing agent. So magnesium is the, let's kind of separate things here. So magnesium, reducing agent. Actually, I think I could, that looks kind of confusing if I put it up there. So let's not do that. Let's put it somewhere else. So let's slightly move this below here. And then magnesium, we're going to say magnesium is the reducing agent. So in this case, it causes something else to be reduced. So it's causing something else to take electrons from magnesium. So magnesium is still being oxidized. Okay, so that's the difference between reducing agent and oxidizing agent. Right? Okay, now let's move on to the next example. All right. Carbon monoxide and water. So in general, if you see more oxygen atoms being added to your molecule, it's probably a good indication that something is being oxidized. So in this case, carbon monoxide is being oxidized to carbon dioxide, and then hydrogen is going from hydrogen in the molecule to hydrogen gas. So that should be something different too. So reactants, carbon. So we look at the reactants, right? Carbon now, like we said before, oxygen's -2 here. So carbon must be +2. So carbon is +2. Oxygen is -2. And hydrogen here, it's still +1, right? Because oxygen and water is -2. Hydrogen is +1. There we go. So that would cancel out the -2 from the oxygen. All right, now if we look at our products, oxygen's still -2 here, but we have 2 oxygen atoms now, so it's going to be -4 in total. So carbon must be +4 to cancel out the oxidation, the negative oxidation state. Oxygen is still -2, so we know that oxygen is not involved. Is neither being reduced or oxidized. How about hydrogen? In the products, hydrogen is H2, but remember, any atom in its elemental form, so hydrogen exists as its own element as H2, so we say hydrogen is 0. So in this case, carbon monoxide. Oh, sorry. Carbon is being oxidized, right? So carbon atom is being oxidized. Here. Okay. So in this case, if it's oxidized, CO is the reducing agent. And then hydrogen here. So we see here hydrogen is going from +1 to 0, and carbon is going from +2 to +4. So we say here then hydrogen is being reduced. So we say in this case water is the oxidizing agent. Okay, so that is that were some more examples. All right, now let's move on to some other examples. Okay. All right, the last not the last, but the third example here is we're going to go over copper solid +2. So the reaction between copper and silver to go to 2 copper 2+ and 2 silver. Okay. So we have a variety of different kind of elements here doing redox reactions. So definitely a very important process. Okay. So remember, copper, and if it's in its elemental form, so for any metal in their solid form, they're going to be, or their natural form, it's going to be 0. So copper here is 0. And then silver here is going to be the charge of the ion in silver, so it's +1. Do not mind the coefficient in front of it. That does not mean it's +2. That just means there's 2 silver atoms, and they each have a +1 charge. +1 oxidation state, okay? So if we look at the products now, copper now will have a +2 charge because now it's an ion, and now silver is in its natural state, so we say that's 0. So if we look at the oxidation states here, we see copper going to 0 to 2+, and silver going from 0 to +1 to 0. So we say copper is being oxidized. So this is a reducing agent. And then silver is being reduced. Silver is being reduced. So this is the oxidizing reagent. Okay? All right, so these are redox reactions. So definitely a redox reaction. So you see redox reaction. So this is also called single replacement reaction, but we'll go into that more details later on. But you see here, on all these cases, they are all being oxidized or reduced because the oxidation numbers are being changed. So we'll go over an example where it's not being the oxidation numbers are not changing. So we'll go over an example in the next video where we don't see that as the case. Okay, so that's it for this video, and in the next one we'll wrap up our talk here on oxidation numbers. Okay, see you then.